centers that were there. The Calcutta center is right now almost dysfunctional. Main center is Institute for Plasma Research in Gandhinagar. So I will talk about there and my own contribution there. And some of these conclusions are very interesting because it doesn't look like that we can learn it in textbook or in our courses. And you have to apply your mind at the spot and come up with solutions. Then I'll discuss a little bit more about international progress. I will also mention about private efforts that are going on, and in particular Project Sunland, which I'm leading in country. And also talk about another method of confinement of plasma called inertial confinement, on which we have got very good results, and then conclude the talk. So what I had said last time, that we want to capture the sun into a box, except that we don't know how to do this, and that is what we have been trying to do for the last 70 years. So I talked about fusion is the process of light atoms uniting to form heavier atoms, but nuclei are charged particles, positively charged particles, so they repel each other. So you need very, very high energy to work on this, and that's why we need to go into temperatures which are like 10 times that of temperature of the sun. Normally we have been focusing on deuterium and tritium plasma as the candidate because that's the easiest one to do at lower temperature and higher cross section. For this purpose, we need to use tritium and deuterium. Both are isotopes of hydrogen. Deuterium is available in water, and whereas tritium is not available, but it can be bred from lithium. I have talked about this, how deuterium-tritium reaction takes place. Deuterium is here. This reaction takes place, and tritium, and then it produces helium as well as neutrons. And neutrons are allowed to interact in the lithium blanket, and they produce helium again, and also it captures energy. And I had also talked about how a simple one bathtub of water and lithium in a laptop battery is enough to power a average household family for 50 years. So very little fuel is required for this purpose. This I did not mention last time. There is a criteria called Lawson criteria, which actually talks about when you produce energy through fusion and the amount of energy that is being lost, what is the minimum criteria which will allow you to have net energy output. That means you are producing more energy than energy that is being consumed. This is called Lawson criteria. Lawson used this to be the product of plasma density and that of energy confinement time. These two products must be greater than some number, and that was called Lawson criteria. More recently, there's a triple product that is being used where actually temperature is also multiplied to this. Now, if you look at these two terms, you have density and you have energy confinement time. So two basic strategies, दो अलग-अलग जो तरीके अपनाए गए हैं, more or less, उसमें एक magnetic confinement है, जिसमें कि हम confinement time बढ़ाना चाहते हैं. We want to increase the confinement time to achieve the Lawson criteria. And the second one is where actually we are trying to increase the density to achieve the same thing. So we have magnetic confinement, we are trying to increase the confinement time, and we have inertial confinement time where we are actually trying to increase the density. So these are the two basic approaches. I'm focusing more on magnetic confinement क्योंकि वो ज़्यादा पॉपुलर है और मेरा जीवन उसमें बीता है, तो इनिशियल कन्फाइनमेंट के बारे में थोड़ा सा बताऊंगा. मेरे ब्लॉग लिखा हुआ है, जिनको इंटरेस्ट है वो देख सकते हैं. मैंने लास्ट टाइम बताया था ranjan.in में. उसमें मैंने पहले ये बताया कि how I got into nuclear fusion research, how did I change my mind to do nuclear fusion research in 1981 when I was going to US. And also there is another blog which combines multiple blogs together talking about my contribution to nuclear fusion, which is being covered in multiple blogs. So those of you who are interested can see these blogs. I talked about three ways that we achieve fusion. One is the start and so on, and that is the gravitational confinement fusion. I also mentioned about inertial confinement, and my focus has been on more of magnetic confinement part. The magnetic confinement, we have talked about linear confinement, magnetic mirror concept, which suffers from end loss. That means some of the plasma particles get lost to the ends. And so then people came up with this toroidal confinement device. Toroidal confinement device, you like a kind of bend that mirror into a toroidal shape. And there are two popular methods of doing this. One is called Tokamak and other is called accelerator. I'm going a little fast because we have covered these things last time. Let me now come to Tokamak concept a little bit more in detail. So Tokamak concept में क्या होता है कि जो हम प्लाज्मा को कन्फाइन करने के लिए मैग्नेटिक फील्ड हमको चाहिए होता है, वो हेलिकल चाहिए होता है। दोनों स्टेलेटर में भी चाहिए होता है और टोकामैक में भी चाहिए होता है। स्टेलेटर में जो हेलिकल मैग्नेटिक फील्ड होता है वो एक्सटर्नल कॉइल, एक्सटर्नल मैग्नेटिक कॉइल से प्रोड्यूस होता है, और जो टोकामैक में है वो दो कॉम्बिनेशन होता है। इसमें जैसे कि ये देखिएगा, ये टोरॉइडल फील्ड कॉइल्स हैं जो कि रिंग की तरह चारों तरफ सजाए गए हैं, और उससे जो है ये मैग्नेटिक फील्ड, टोरॉइडल मैग्नेटिक फील्ड प्रोड्यूस होता है जो कि टोरॉइडल डायरेक्शन में है, इसलिए इसको टोरॉइडल मैग्नेटिक फील्ड कॉइल कहते हैं। और इसके साथ क्या किया जाता है कि इसमें मान लीजिए आप हाइड्रोजन प्लाज्मा क्रिएट करना चाहते हैं, तो हाइड्रोजन प्लाज्मा, हाइड्रोजन गैस भरते हैं उसमें, यू फिल द वेसल, सो देयर इज अ वैक्यूम वेसल, यू evacuate that vacuum vessel to very high vacuum like 10⁻⁸ or ultra high vacuum जिसको बोलते हैं, and then you fill that with hydrogen gas, very pure hydrogen gas, and through transformer action you produce electric field along the direction of torus. The electric field actually, if it is sufficient, if it is high enough, it will break the gas into electrons and ions, just like we see discharge. So actually you produce this plasma through the electric field, and then in response to electric field, the plasma becomes conducting. When the hydrogen breaks into electrons and ions, it becomes conducting, and current starts to flow. That's called current, plasma current. So the plasma current starts to flow in this direction. The magnetic field produced by plasma current also becomes very high, is in this direction, in the poloidal direction. So you have two magnetic fields, one is in toroidal direction and other is the poloidal direction. These two together actually form the helical magnetic field lines. So this is how the tokamak works. Now the problem with the tokamak is that it is a device that is pulsed in nature, because of the fact that to drive this electric field you use transformer action, and that electric field cannot be maintained continuously like this. So it is a pulse. We try to get it to a very long pulse, and there are now new methods trying to maintain this plasma continuously. In the accelerator methods, actually, you don't require this pulse nature. It is a continuous thing. The accelerator has an advantage, but accelerator is a very, very complex. But just now, today, before I started this talk, we got the news that even accelerator has achieved temperatures twice that of the sun. So that is another very hopeful confinement device, accelerators. And recently there have been more progress in this. I'm going to talk about it later. So tokamak basically depends on two magnetic fields, one being produced by external magnetic fields, I talked about that, and the other being produced by plasma current. When the plasma current is flowing through, then it also heats up, just like any resistance. When you flow a current through that, it heats up. Similarly, plasma also heats up in this. But there is a limit to that heating. So as we are showing in this, the electric current, plasma current is flowing through this, and that heats up the plasma. That is called ohmic heating. Okay. And just like Ohm's law, we have heard of Ohm's law. So similar to that, this heating takes place. But as the plasma heats up, it also starts to radiate and lose energy. So at some stage, there's a balance between the amount of heating that is taking place and versus the amount of energy that is being lost. And you can't increase the temperature beyond that. So how to then take it to temperatures like what we have achieved already, like we are talking about 10 times that of the temperature of the sun, about 15 to 16 crores. उस टेम्परेचर को ले जाने के लिए हमको अलग अलग और भी मेथड यूज करने पड़ते हैं. Like, for example, radio frequency heating is one technique by which you dump in huge amount of megawatts of power inside the plasma using antenna. At the same time, there is another technique called neutral beam injection heating. The neutral beam injection heating, actually, you take hydrogen atoms, you ionize them, and then accelerate the ions to very high energy, and then again neutralize them, and that high energy beam can penetrate through plasma and transfers its heat. So these are the two popular methods of heating the tokamak plasma to very, very high temperatures. So normally ohmic heating, it starts with ohmic heating, and then we use one or both of these techniques to heat the plasma to very high temperatures. In India, as I mentioned, the work started in 1980s. In 1980s, the work that started, there were two machines being built. One was in Calcutta Science Institute of Nuclear Physics, and the other one was in Institute for Plasma Research, Gandhinagar. So SINP Tokamak was the one that was made in Calcutta. It was designed. It was fabricated by Toshiba and installed in Calcutta in 1987. The other machine, Aditya, as you understand, is name of the sun. Aditya सूर्य का एक नाम है, तो उसी के ऊपर में ये नाम रखा गया था आदित्य. आदित्य 1989 में ऑपरेशनल हुआ. 1989 में ये जो यहाँ पर 0.30 मीटर्स लिखा हुआ है, 30 सेंटीमीटर्स, ये मेजर रेडियस है. मैं स्लाइड को थोड़ा पीछे करके समझा देता हूँ. ये जो मेजर रेडियस है, इसके सेंटर से, इसके जो सेंटर है, सेंटर से लेकर जो मिडिल में इसका जो रेडियस है, उसको मेजर रेडियस बोलते हैं. टिपिकली इसको आर बोलते हैं. और ये जो पोलोइडल क्रॉस सेक्शन है, इसका जो रेडियस है, उसको माइनर रेडियस या अक्सर उसको ए लिखते हैं. तो ये मेजर रेडियस आर है और माइनर रेडियस ए है. तो यदि हम साहा इंस्टीट्यूट की मशीन को देखते हैं तो 30 सेंटीमीटर उसका मेजर रेडियस था और आदित्य का 75 सेंटीमीटर मेजर रेडियस था. 7.5 सेंटीमीटर SINP मशीन का माइनर रेडियस था और 25 सेंटीमीटर माइनर रेडियस आदित्य. तो आदित्य SINP टोकामैक मशीन के कंपैरिजन में काफी बड़ी थी. मैग्नेटिक फील्ड थोड़ा सा बड़ा था SINP टोकामैक, 2 टेस्ला 20 किलो गॉस और आदित्य का 1.5 टेस्ला था. तो दोनों में तो आदित्य काफी बड़ा था कंपेयर टू SINP मशीन. और भी डिफरेंसेस थे लेकिन उसमें नहीं जाऊंगा. तो ये जो है, ये साहा इंस्टीट्यूट ऑफ न्यूक्लियर फिजिक्स कलकत्ता में जो SINP टोकामैक सेटअप किया गया था, जो कि तो छोटे साइज का था. इस पर मैंने 9 साल काम किया था. 1986 में यूएस से PhD करके वापस आया था और मैंने कलकत्ता ज्वाइन किया था. तो वहां पर इस मशीन पर मैंने 9 साल काम किया था और गांधीनगर में मैं 7 साल मैंने काम किया था. तो मैं दोनों के बारे में ब्रीफली थोड़ा सा बताऊंगा. तो एक ब्लॉग, जो मेरे काफी सारे ब्लॉग हैं जिसमें आप जो यूजर्स हैं वो देख सकते हैं, ऑडियंस देख सकते हैं. पहले मैंने जब 86 में ज्वाइन किया तो ये जो मशीन आ रहा था तोशिबा से, उसमें डेटा एक्विजिशन कंट्रोल सिस्टम नहीं था. देयर वाज नो वे टू कलेक्ट डेटा फ्रॉम द मशीन and the machine discharge was a very short time. So I developed data acquisition and system for that machine, which was used in 1987. उसकी स्टोरी है इसमें, how Japanese got hooked on to Indian technology. जो पहले वो जापानीज मेरे टेक्नोलॉजी पर विश्वास नहीं करते थे, फिर उनको जब उन्होंने ट्राई किया तो काफी पसंद आया. उसके बाद से मेरा सिस्टम उसमें चालू हो गया. फिर इसमें मैं एक्चुअली जब PhD कर रहा था, when I was doing PhD in nuclear fusion in US, I'm the first PhD probably from this country nuclear fusion. और मैंने 1981 में यूएस गया था, 1986 में PhD करके वापस आ गया था इंडिया. तो उस टाइम मैंने मॉडलिंग किया था और वर्ल्ड के फास्टेस्ट कंप्यूटर्स पर काम किया था. I was working on the fastest supercomputers of the world, Cray 1, Cray 2. I was not an experimentalist, but this blog actually talks about how I became an accidental experimentalist because our modeling was giving results and nobody was willing to actually try out what I wanted them to do to clean the machine. This actually talks about how I became accidental experimentalist. 95 में मुझको रिक्वेस्ट आया कि इंस्टीट्यूट ऑफ प्लाज्मा रिसर्च गांधीनगर में शिफ्ट होने की. वहां पर एक सुपर कंडक्टिंग मशीन बनाई जा रही थी, SST1. Then I shifted to Gandhinagar in 95, and so this is the Aditya Tokamak. You can see it's a much bigger one in size. The hall is also much high, it's about 3 floors high, and there are surrounding buildings also to accommodate all the systems and subsystems. So I've written a blog how when I moved to Gandhinagar in 1995 August, and then how this machine, which was not working properly for 6 years, I could get it to work in 5 days. So this talks about 5 days miracle nuclear fusion reactor Aditya Tokamak. After that, I was made project leader of this reactor Aditya Tokamak till 2002 when I moved out of Institute of Plasma Research to join a university. This particular blog talks about how there was a problem of grounding system, and using a technology that I have seen in my village, how I could improve the system, and that led to discharges. We had to have 80% discharge failure, but that could be solved, and then we started to have 100% success in the discharges. So this blog talks about that. Then at one time there was a big failure in the machine that meant that we would have to take out the whole machine, disassemble it, and we may not be able to put it together. Then I saw a photograph. The photograph is shown here. Seeing that photograph, something came to my mind, and then within 15 days time, without disassembling this machine, we could take out the part which had failed this particular system called TR1. This was a 1.5 ton solenoid magnetic field. This was a crucial part. This was the heart of the machine. We could take it out without disassembling and repair it, put it back. So this block talks about this. And to take it out, I had to make a jugaad. You can see what I have used is Tata pickup truck 420 brake shoes, and combine this to take it out. That is the story of that block. When we took out that machine, that solenoid, you can see it's lying on the ground, and all of us are happy there. Then I also understood there were a lot of magnetic error fields that we talk about, error fields. We solved that mystery also when we took out that is this blog talking about that. Then once we saw suddenly a lot of sparks happening in the machine. There was no insulation failure, there was a lot of sparks, it was like a ghost. We were very perplexed. Finally, we could actually find out the problem, and we had to actually, it was due to grounding. It was like a ghost was moving around. Sometimes they were discharged here, sometimes they were discharged there. We were all perplexed. So this is the story of that. Then this is a story about how in December 1999, there was a sudden accident, and the machine, when it was operating, normally there's a sound. Suddenly that sound became silent, and what had happened was 2 coils had broken apart from its support and got thrown out. So we learned from this what lessons, every scientific mission has success and failures, and both are important. We learn from failures and also from success, and that's the important part of the scientific research, because every time you may not be successful. So this accident gave us a lot of insight into the problem that happened. So this machine was operational till about 2014 or so, and then it was decided that this machine will be upgraded, and it's been now upgraded from Aditya to Aditya upgrade. And main change has been in the vacuum vessel, which was of square cross section. Now it has been made into circular cross section, and also the plasma cross section. There is a concept of diverter that I'm not able to go into that. That concept has been also brought into this. This is performing very well now. Have been resolved in this while the machine was totally disassembled and put back together. So in 1995, around 1994-95, when I was requested to move to Gandhinagar, in Calcutta, I was planning a superconducting machine, and then Government of India approved a superconducting Tokamak project in Gandhinagar. There were 2 machines. One was called SST1, that is shown here, and there was another machine called SST2 that is not shown here. These 2 were approved at the budget of 800 crores rupees. So I was requested to shift to Gandhinagar. So August 95, I moved. I was requested to work on both the machine, the SST1 that was under design and the Aditya machine, which is operational. And I could get the Aditya to operate, and I was project leader of that, and I was also project leader of SST1 operation and control group. That time, there were 4 machines being planned, and all of them in Asia, all 4 superconducting machines. So one of them is East in China. I'll talk about this performance. In fact, some of the results that we have been talking about has come from this. In Korea, there's a K-Star. South Korea, there's a K-Star. And Japan was planning a very, very large machine called JT60SA. This JT60SA had just been operational last year, whereas East and K-Star became operational much earlier. Let me compare the 3 machines, East, K-Star, and SST1. These 2 became operational in mid-2000s, and JT60SA of Japan, which is a very big machine, had just become operational last year. So I will just compare the ones which became operational in mid-2000s. So this is a view of the SST1 machine. As I said that I was project leader of the operation control group, and so the control system, real-time control system that I designed has been used in this. And ITER concept that Gaganji talked about, International Thermonuclear Experimental Reactor, that actually is also using the same concept of real-time control that I had designed for SST1, which was based on digital technology. I designed this around 98, 99. And that has been used as SST1, and also same concept has been borrowed in ITER project. So I compare these 3 machines. If I look at SST1, East, and K-Star, major radius of SST1 slightly smaller compared to other 2 machines, 1.85 to 1.8. Minor radius of SST1 is also a little smaller compared to the other 2 machines. The SST1 became initially operational in 2005, But there were technical problems. Because of this, it had to be disassembled again and reassembled in 2013. So from 2013, really it started to work. 2005, the assembly had technical problems. Around same time in China, East started work in 2006 and 2007 in K-Start. The plasma current values that were designed, this was for 0.2 megaampere SST1, they achieved 100 kiloamperes or 0.1 megaampere. In East, 1 megaampere was designed, they achieved 1 megaampere, so full achievement here. And in K-Star, 2 megaampere is planned and they've achieved 0.35 megaampere so far. If I compare the timings, the time duration for this was planned, SST1 was planned for 1000 seconds, East also for the 1000 seconds, and K-Star for 300 seconds. Unfortunately, the SST1 has not performed well in this. It's not even able to cross 1 second. Whereas China has achieved 101 seconds with 120 million degree temperature and 20 seconds with 160 million degree temperatures. And the Korean machine has achieved about 72 seconds with 100 million degree temperature. And in terms of temperature, also SST1 has not performed well. So out of 10 million expected, it has only reported 2 million degree temperature. So you can see that the Chinese machine has performed very well. It has set the world records. In fact, just a few weeks ago, and 100 million it has achieved in 2018. K-Star achieved in 2020. So that is the story of the 3 machines that were planned in mid-90s. Now, what is happening is that because of certain technological development that are taking place, such as high temperature superconductors. I will talk about this. We have just had a news just a few days ago, which actually also allow you to produce a very, very high magnetic field. High temperature superconductors are those which can work at liquid nitrogen temperature as compared to liquid helium. So normally superconducting state में किसी मटेरियल को लाने के लिए हमको काफी ठंडा करना पड़ता है. लिक्विड हीलियम जो कि लगभग 4 डिग्री केल्विन या -269 डिग्री सेंटीग्रेड होता है, वहां तक ले जाना पड़ता है. लेकिन जो हाई टेम्परेचर सुपर कंडक्टिंग मटेरियल होते हैं उनको लिक्विड नाइट्रोजन टेम्परेचर पर ही हम काम कर सकते हैं, 77 डिग्री केल्विन, जो कि रिलेटिवली आसान होता है. यू मस्ट हैव सीन लिक्विड नाइट्रोजन बीइंग यूज्ड फॉर ऑक्सीजन, आइसक्रीम एंड मेनी अदर थिंग्स. यू विल सी लिक्विड नाइट्रोजन tankers moving around. So many purposes in industry it is being used. So it's not as costly. Other development that has happened is advanced manufacturing, such as additive manufacturing. And I tried to promote this in India in 2014, 2015 and so on. And Atal Tinkering Lab was outcome of this. In 2016, Niti Aayog announced Atal Tinkering Lab, and Atal Tinkering Lab was set up in schools. Now actually I'm chairing a committee of AICT to set up idea labs across the colleges and higher education institute. And so this is part of this is additive manufacturing. This is also helping extremely high power superconductor computing modeling. So supercomputers, very fast supercomputers. I was using Cray 1, Cray 2 in 1980s that were considered very fast. But today we have so much faster computers compared to what we had. This is also very helping. One more interesting thing that has happened is artificial intelligence-based algorithms. They have also been helping. So there are a number of technological advancements that have happened because of this. Today it is starting to become possible to actually achieve nuclear fusion in a smaller machine at a lower cost. And because of this, actually what is happening, investments in privately funded fusion ventures has grown. तो जो प्राइवेट फंडिंग है ये फ्यूजन न्यूक्लियर फ्यूजन में काफी बढ़ गया है लास्ट 20 साल में. 20 साल पहले 1 आध 2 हुआ करते थे, अब जो है लगभग 20-25 प्राइवेटली फंडेड प्रोजेक्ट हो गए हैं. उसमें इंडिया में भी स्टार्ट हुआ है, जिसका चीफ मेंटर मैं हूं. मैं उसके बारे में आप लोगों को बताऊंगा थोड़ा. I'll talk about what we are doing in India in this regard. So if I show you a table here, I will talk about Project Sunlayan, which I am the chief mentor of that, and what we are trying to do that. But you see Commonwealth Fusion Systems, this has been set up by MIT US as a spin-off, and this was set up in 2018. And this had funding of $264 million. Similarly, there's 282 million General Fusion, TAE Technology, Los Angeles, this has been working for 1998. $750 million, out of that $150 to $200 million has come in last 2 years. Okay. Similarly, other machines, in fact, Tokamak Energy, another one. In UK, I was talking to Melanie. She is the communication director of that yesterday, and they have had investments of about $87 million. So similarly, there are other machines also that are being, so all of these are through private investment. And for the first time in the country, in India actually, through private investment, we have started Project Sunland. जैसा मैंने पिछले बार कहा था कि न्यूक्लियर फ्यूजन को हिंदी में नाभिकीय संलयन भी कहते हैं, नाभिकीय संलयन कहते हैं, और जो न्यूक्लियर फिशन होता है नाभिकीय विखंडन होता है। नाभिकीय विखंडन उसमें तोड़ते हैं न्यूक्लियाई को, और नाभिकीय संलयन जिसमें जोड़ते हैं। तो इसलिए इस प्रोजेक्ट को मैंने नाम प्रोजेक्ट संलयन दिया है, और ये फर्स्ट प्राइवेट इनिशिएटिव इस टाइप का इंडिया में आज तक किसी ने ऐसा ट्राई नहीं किया है। और न्यूक्लियर फ्यूजन जैसा मैंने बताया कि अभी केवल इंडिया में एक ही नेशनल लैब इंस्टीट्यूट ऑफ प्लाज्मा रिसर्च गांधीनगर में काम हो रहा है। उसके बाहर ये पहली बार ऐसा हो रहा है कि किसी भी जगह पर न्यूक्लियर फ्यूजन प्रोजेक्ट स्टार्ट हुआ है, और ये मेरा फॉर्चून था कि मैं इसके साथ एसोसिएटेड हुआ एज ए चीफ मेंटर। और इसको स्टार्ट करने के पीछे डॉक्टर आकाश सिंह, जो कि खुद इन्वेंटर हैं और इन्वेस्टर भी हैं सिलिकॉन वैली में, उन्होंने एक अल्बॉट टेक्नोलॉजी प्राइवेट लिमिटेड पुणे में सेटअप किया। डॉक्टर आकाश सिंह वाज ए इन्वेंटर एज वेल एज इन्वेस्टर। ही सेट अप अल्बॉट टेक्नोलॉजी प्राइवेट लिमिटेड इन पुणे, एंड अंडर माय मेंटरशिप दिस इज बीइंग न्यूक्लिएटेड माय यूनिवर्सिटी राइट नाउ, डीवाई पाटिल इंटरनेशनल यूनिवर्सिटी, Akudi campus of Pune. DY Patil is many campuses. This is in Akudi campus of Pune, where I am vice chancellor. And actually, we've started the work, the design work, and the planning work is going on. Number of scientists and engineers have joined this. As we plan to raise about $10 to $20 million for the first machine, and then if we are successful, we'll keep on improving it further through further investments. Recently, I've had discussion with Maharashtra government. They're trying to get some help in terms of policy support and land and so on. What we are trying to do in this case is to develop nuclear fusion technology in India at very cheap cost, just like in IT sector. We did this with lower cost. We could actually develop IT technology at 1/15 to 1/20th. We are trying to do the same thing for nuclear fusion. Now our target is two. First target is to use nuclear fusion as a what is called volume neutron source. That means we try to produce neutron through deuterium-tritium reaction. And second is long-term goal is energy solution. So energy solution, you need to have net gain of energy, whereas the neutron source, we don't need to worry about net gain of energy. What we need to worry about producing neutrons economically. If we are successful in this, then we want to apply this to three possible scenarios. One is medical isotope production. There is severe shortage in the world in medical isotope. Even India, many facilities that are there, they are not able to get medical isotopes because of severe shortage, and worldwide this shortage there. Second thing in which India is very fortunate is to have thorium. India has 25% of the world's reserves of thorium in India. What we are trying to do is to use the neutron source to convert thorium to uranium. I talked about this last time, from thorium-232 to uranium-233, we want to convert this. So from thorium is fertile fuel. I talked about fertile versus fissile. We convert thorium, which is a fertile fuel, we convert this to fissile fuel, which is uranium-232. And then this can be supplied to the nuclear power station that are existing based on fission. So this combines fusion and fission. Fusion is used to produce neutrons, and neutrons are used to produce fissile fuel. So that's why this concept is also called as fusion-fission hybrid. Fusion-fission hybrid. Nobody in the world is working on this, so we are trying to do this. And similarly, the same neutrons can also be used to produce processed radioactive waste. Because I had mentioned this last time, that when you have nuclear power station, there's radioactive waste produced. That's a very, very long half-life of 100,000 years. You can process that, reduce the half-life to 100 or 200 years, and at the same time produce energy. So this is our first goal. This is the producing volume neutron source. And then as we go along, we need to make larger and more powerful machine, which will actually lead to long-term energy solution. So right now we are targeting on producing neutrons economically, and then next target will be energy solution. So we are making a small machine first, which is to just try it out and have a prototype. And this I'm using the concept we are planning is modular spherical tokamak that we're going to try. Again, this has not been tried in the world anywhere. So we are going to try this for the first time in India, in Pune actually, which is being nucleated at my university. Similarly, MIT, USA, I mentioned about this Commonwealth Fusion Systems. In 2018, it was set up. And this concept that they're working on came out of a student project. A group of students were working on this. They came out with a concept called ARC. And Spark is a small version of this called smallest possible arc. Smallest possible arc. This is using high field, high temperature superconducting magnet. This is a very, very important development that is there. And their goal was that starting 2018 to 21, in about 3 years' time, their goal was to develop and test large bore STS magnet. Bore means the hole in the center. So it has to be a very large hole that is required for the tokamak kind of work. And recently, just about 10 days ago, they reported success in this. I'll just share a news with this. Now that they have success in this, this was their first target. Then they have already designed the machine. They will start the construction of this and take about 4 years to construct the machine. And based on the ARC, actually, success of ARC, the Spark, they plan to in early 2030s, they want to make the ARC, which will be in similar size, similar performance as ITER, but much smaller in size and much lower cost. So ITER is like 30 meters in height, about 8 to 9 floors height. ARC will be much smaller, but have similar performance as compared to ITER. And it may happen that before ITER, see this first nuclear fusion reaction, which is expected in 2035 or 2036, ARC may start to produce nuclear fusion as an energy source. So this is a major development that is taking place. And this is the news that came, just you can see this news is actually September 9th, just about 10 days ago. Fusion startup builds 20 Tesla superconductor. This is considered the highest magnetic field produced for through these large bore magnets. This has been successfully demonstrated. There was another news around 2014 or 15 by a company called Lockheed Martin. They have a division called Skunk Works. They had claimed that truck size 100 megawatt nuclear fusion plant they can make. And in 5 years, they plan to actually make the prototype and then in 10 years commercialize that. But it has not, their promises have not been kept, and it has the project has suffered problems. But this was interesting news when it happened about 5 years ago. I talked about accelerator. This Wendelstein 7X accelerators are very complex to make, but because of the fact that we are able to produce, manufacturing has improved, precision machining is improved, we are able to make these devices, Wendelstein 7X, after 10 years delay. In Germany, it has been made. It's a complex device, but as I said that today in accelerator also performance is improving. We have achieved twice the temperature of the sun in accelerators, and it has the good point that it is a continuous machine. That means you don't need to pulse it. It's a continuous machine. So Wendelstein 7X is a good accelerator example. I'd also talked about inertial confinement, which laser confinement is part of this. And I'd said that Lawson criteria is there, which is multiplication of electron density and that of energy confinement time. So people are either trying to increase the confinement time or trying to increase the density. So this inertial confinement, laser confinement or laser fusion is an example of that. Depends on the high density part. So whereas in other cases we use gas, in this case solid pellet of deuterium tritium is used, and from all directions, high beam laser is hitting this at the same time. The pellets are very, very small, and that actually the amount laser beams and the laser produced X-rays rapidly hit the surface of fusion target. That DT pellet, very small pellet is there, and the fuel is compressed by this blow off of hot surface material, and through this process nuclear fusion takes place. Just to give you an example, I'm not going into too much detail of this. You can see this is a machine National Ignition Facility in Lawrence Livermore, NIF as it's called. There's 192 laser beams. You can see the size of laser beams. There's human beings standing there, very small compared to this. and you can see the length through which is going. And this is the target chamber. This one is the target chamber in which all these 192 beams are coming in. And they actually concentrate on a very, very small pellet at the center. The pellet size, you can see this eye, human eye compared to that, a very small pellet is there. This pellet is actually dropped, and suddenly from all directions, these 192 laser beams come and shoot at this. It's very, very important to have that alignment properly so that all of them are synchronized perfectly and hit it from all directions in billions of fraction of second. And this success recently, the success story has come is that NIF achieves breakthrough in laser fusion. They have been able to what is called ignition point. They have demonstrated they have achieved ignition point, but for a very brief moment, as I talked about. So another concept where actually you don't use something like deuterium, which produces a neutron. This is called aneutronic fusion. There are a number of reactions that are possible. And I will just highlight one that is called proton-boron reaction. Proton-boron reaction, PB11 reaction, in which no neutrons are produced. So there are sometimes what happens, the neutrons escape out of the reactor and they go and strike the structure that is surrounding it. And due to this, the structure starts to become radioactive. Aneutronic fusion has advantage, but the temperature requirements are much, much higher. Instead of 100 to 200 million, it is actually 2 billion, 2,000, roughly 2,000 million. So about 10 times that of required for DT reaction. But people are trying this, and there's a company called PB11.com. They have a website in Australia. We have had some discussion with them. They are working on this concept. So in this case, actually, you have the proton and boron reacting, and the net outcome is actually helium's carrying energy. There's no neutrons in this. In other cases, we have seen neutron and helium carrying out. There is no neutrons in this. So there's absolutely no nuclear waste in this case. It's a very, very clean source of energy. There's another company called TAE Technology that's been in operation from 1998. They have raised more than $750 million. Last 2 years, they have got $150 million. They have demonstrated very good results recently in last 2 3 years in a machine called Norman, and now they're planning a machine which is called Copernicus, and this will demonstrate a reactor type performance. This is using slightly different concept. It is not Tokamak concept, it's slightly different concept. In this particular TAE technology, actually, Google has provided artificial intelligence-based algorithm that has allowed them to actually optimize the machine performance very well and gain a lot of energy, which was not possible otherwise. Now, in addition to nuclear fusion, for energy purpose, as I talked about, one can produce medical isotope. So there is a company called Phoenix Nuclear that's working on this. Similarly, there is also chances of this being used for space. So fusion can enable really interesting robotic and human missions to Mars and Pluto. Also potentially a way of getting into interstellar space. For deep space exploration, fusion is also an interesting energy source and propulsion source. And actually, I have been talking about asteroid belt. The asteroid belt is between Mars and Jupiter that has so much mineral wealth, that if you divide among all the people on the Earth, everybody will get $100 billion. So tremendous. So actually, there is a space race that is happening. You might have been seeing about Elon Musk and Virgin Galactic and so on. People are going into space, and these are private entities. And then there's a huge wealth that is lying in the asteroid belt. And all of this may be possible through fusion-based propulsion system. Similarly, what is happening as the progress in nuclear fusion is happening, the different governments, UK, USA, other governments are trying to actually promote fusion energy-based industry. And like this is UK government's 10-point green plan as part of supporting fusion. Similarly, US has an Infuse program and other programs that are there. So all the countries are trying to attract industry to nuclear fusion so that in next 10 to 15 years, when it becomes possible, they can take advantage of this. So this is a machine called a step fusion power plant that UK is planning to have by 2040. So to end the talk, nuclear fusion has been making headlines recently, and every day we see new headlines. Like today I saw a new headline about accelerators having reached temperatures double that of the sun. It is showing that we are moving closer to its realization. For the last 70 years, we've been talking about this, that in the next 20 years we'll achieve this, but actually we have not been able to do that. But now it looks more possible than ever that in the next 15 years or so we should be able to achieve this. As I mentioned, that private investment in nuclear fusion around the globe is growing, and we believe that with 4 decades of experience, in India we started the work in 1980s, early 1980s, India can develop technology, nuclear fusion technology at much cheaper cost in Western countries like we did in IT sector, but we need to have proper partnership and we need to have proper government support in terms of policy and incentives. So I am very happy, that first time in India in nuclear fusion we have private initiative, and I'm lucky to be the chief mentor of this. It is being nucleated in my university, and it's a very happy occasion because very uncertain technology that we are working on. But government, as I mentioned, government must come out with clear policy and incentive to promote nuclear industry in India. And actually, on common people, in mind of common people, even policy makers, nuclear word only makes nuclear fission. So they get worried about bombs and other things. But nuclear fusion industry is a safe industry. It doesn't have issues of meltdown and so on. So actually, one can promote in a much easier way. And so I would request through this channel that government must look into this and not to mix fission and fusion, and actually make sure that nuclear fusion industry can grow in the country. So I will stop at this point, and thank you so much for listening patiently to my talk. Thank you so much.
Thank you very much, Professor Prabhat Ranjan. We really enjoyed your enthusiastic and exciting talk on nuclear fusion research as well as the Indian scenario on it, and more startlingly the partnership of partnership from the private industry on this talk. We like to listen you again and again on this kind of talks again on some similar issues, including more about the inertial fusion machines. We have some questions. If you allow me, sir, can I ask? Can I take up those questions one by one, please, sir?
Yeah, please.
A student question first. Sir, suppose if a MSc student in either in physics or in chemistry wants to take up his career or her career in nuclear fusion research, may be inclined towards the private partnership systems, private systems. What kind of topics or what kind of subjects one must choose during the master's program or undergraduate program probably? Please, sir, your comment.
Thank you so much. Thank you. It's a very good question. Because we need a lot of young people to come into this field. And we have had nuclear physics course in India for a long time. But nuclear physics is only focused mostly on nuclear fission part, not in fusion part. But last 10-15 years in India, many places are there. And the nuclear physics courses, both fusion and fission, are being taught now. So there are a number of universities, in fact, in Gandhinagar, for example, Pandit Dindayal Petroleum University, and now it's called, I think, Pandit Dindayal Energy University. They're also there teaching. There are a few other places also in the country they're teaching. So those who want to come from the physics side of it, they could take nuclear physics and make sure that there is specialization on nuclear fission, they should go into that area. There's a lot of online material also available on this from various sources, including Tokamak simulator, where you can go around and do virtual experiments. That is also available online. Second is that any technological development like this requires input from multiple technologies. So it's not only that physics people work on this, it's also engineering people, whether it's electronics, it's computer science, whether it's mechanical, whether it's electrical, vacuum systems. Different people from different sectors combine into this. So in Institute for Plasma Research, for example, there should be a technical training program. I'm not sure that it's running still. But actually we should take people from different fields, train them for 1 year, just like BARC training school. And so if you get selected in that, and if you're successful in that, you should be absorbed in the Tokamak project, SST1 project, and other projects that are going on. So you could come from many fields, but then you have to focus your effort on nuclear fusion. So both, either if you want to come to science background, you could take a master's in nuclear physics with specialized in nuclear fusion, or you can come from engineering background also and participate in this. Both the possibilities are there. Thank you.
Thank you. Yes, I myself is a student of nuclear physics during my MSc, and then I did my PhD in the interacting areas of nuclear physics and spectroscopic lasers. And as I remember that the nuclear fusion research is very important for development of new lasers called the gamma ray lasers, which are used, which are supposed to be used greatly in astronomical researches, etc. Yes, so now coming to the astronomical researches, sir, you talked about the magnetic confinement, you talked about the inertial confinement a little, but then you, I remember that last time in your initial talks, you talked about the gravitational confinement, which is the usual practice, usual process in the stellar processes. So when we do it, this question I am getting from YouTube, that when we do this exercise either through magnetic confinement or through inertial confinement, does this gravitational confinement mechanisms interfere into that, or how it is?
No, not at all, because the mass that we are dealing with on Earth is much, much smaller. You can imagine this amount of mass the Sun had is huge. So that's where the gravitational confinement takes place. And the forces are gravitational forces large enough to keep the plasma confined. On the Earth, that masses that we are dealing with is very small, so it doesn't really matter.
Yes, secondly, in the similar concern, somebody else has asked that is the condition for the Lawson criterion is equally valid in the case of the inertial confinement, because the two mechanisms are slightly different when we try to reach. The magnetic confinement is dealing with the time, and the inertial confinement is primarily dealing with the density. Sir.
Actually, as we saw, the Lawson criteria was based on product of two parameters. One was electron density, other was energy confinement time. So the two approaches take two different approaches. One tries to increase the energy confinement time, that's the magnetic confinement concept, and the other one works on increasing electron density, that is inertial confinement. So both of them deal with the Lawson criteria, and they do it by approaching the two parameters. One is trying to increase the electron density, another one is trying to increase the confinement time. So both of them follow that. And now, as I mentioned, there's a triple product that is used, which is not only.
How do you feel out of all those things, sir, professionally and academically, sir?
So to be frank, are you able to hear me, please?
Yes, yes, we are. Yes, sir.
So I had moved out of active nuclear fusion research from National Labs in 2002, and while I was associated through some projects, when I was in Delhi as heading India's technology think tank TIFAC, close to NCRT, as I mentioned last time, it was on the same road, gate number 2, that you have
yes,
your
sir.
road.
Yes, sir. Yes, sir.
And every day I used to cross that road in the morning, your gate in the morning and evening. So there actually, as head of India's technology think tank, I was tracking the progress in nuclear fusion. And at national level, I was trying to push the agenda to make sure that the government of India and others pay attention to this. But I was not very successful, although we had tried in many occasions. But I had never expected that I will come back into nuclear fusion in an active way. It's a matter of chance, and I feel lucky that I got this opportunity to come back in nuclear fusion at a stage when the prospects are very high of achieving this in next 10 to 15 years. And if you hear some of my talks on India Science and so on, I used to talk about this from Delhi, but I have now got hands-on into this. I feel very lucky and happy to be part of this, and I hope to contribute into this and bring India into a world map. And I just, in my talk on last Friday to Deputy Chief Minister Ajit Pawarji, I mentioned that we would like to make Pune to be on the world map of nuclear fusion. So he's responded very positively, and I'm hoping to follow up on this and then make sure that what we are doing in the university that nucleated takes a big shape. So we already have some funding, $1 million started, and more funding will be arranged.
So yes, sir, we like to see you inside the NCRT campus, not only after, just passing through the gate number 2 of our campus. Now my colleague CV Shimre also would like to ask a couple of questions to you. Quick questions, sir. Shimre, please.
Thank you. Last but not the least, being an environmental educator, sir, I just want to know something related to this production of energy. India is quite progressing well, I would say, in the sector of renewable energy, especially in solar energy sector. So do you think we really need such a complicated technology such as nuclear fusion and investing so much in this field to get that energy?
Right. That's a very, very good question. Thank you so much for asking this. Actually, this is a common question that is asked because India is making huge progress in renewable energy. We're setting up some of the largest solar power generating setups across the country, and it has speeded up over the last several years. But and the cost of solar cells have come down tremendously. But actually, both solar and wind are uncertain energy sources, and so what is required is that you need to have a base source of energy which is not fluctuating, and then on top of that the renewables can add on, because to store renewables you require huge amount of battery, which is not possible, and so you need both. You need renewable, but the base load, which nowadays is provided by mostly coal, and then you have 60 to 70% base is provided by power is provided by coal, and then a smaller percentage by nuclear and so on. So on top of that, only you have the renewables that are beneficial. So you need to actually make sure that that base energy that can be produced nuclear fusion as a continuous source of energy, and on top of that you add renewable. So both this combination is important. And as I said that, while the cost may be prohibitive, looks like prohibitive, but for nuclear fusion to be success, it will only be successful if the cost of production of energy is less. It is very high, of course, it's not going to be useful. It has to become less. But any technology which develops in the beginning is costly, and later on the cost starts to come down. So that's the same thing we're expecting in this. And so we believe that the nuclear fusion will start to provide a sustainable source of energy for a long, long time to come, and the renewable energy will be on top of that. So both these combinations will work fine. Thank you.
Yes, I remember a bathtub and a small lithium-ion battery will work for 50 years for a family, average size of family. Professor Ranjan, we are indeed very much thankful for having you here in our platform. We also thank the mentors of the D.Y. Patil International University for making NCERT eligible to get Professor Ranjan's talk on this platform, on this PMeVIDya channel's platform, which is being telecasted live at this moment. We really look forward for having a long association with D.Y. Patil University in future too, and you made the mention of Dr. Akash Singh, an entrepreneur. Would like to have interaction with him sometime.
Sure.
So thank you very much, Professor Ranjan. I'd like to meet you again.
Thank you so
and
much.
again
Thank
and
you so
again.
much for being
And viewers, next time we are here on this Friday again with another exciting talk on by Dr. Sahana Singh. She will be speaking from Houston under our program, the same program, Listening to Learn series with Pravasi Bharatiya Academic and Scientific Sampark, called Prabhas, under its National Student Outreach Program. So Dr. Singh will be talking about India's relevance, the relevance of India's heritage, educational heritage in today's context. So looking forward meeting you all again on Friday at the same time, 10 o'clock. Thank you very much. Thank you all.